Hello everyone, this is Amar Rapai, and today I will talk about a new algorithm developed together with researchers from Los Alamos National Lab, Boram and Nga, and also Xia Cheng Chang from the UC Berkeley. The title is Lossy Compression of Statistical Data Using Quantum Annealers. Uh, the paper is on the archive, hopefully today, so you should be able to see it. So, the introduction. This talk is focused on scientific computing and data, but can be applied to any kind of data in general. The focus is for high amounts of data, specifically for lattice QCD that we just heard a talk about. With modern simulations, we can generate huge amounts of data, here in the order of petabytes. And similar, you can have big data from business. However, when you have statistical data, few significant figures of the data should be representative and should be required for analysis. In other words, among all the noise, there are correlations in the data that is what you're trying to extract. And you can make use of that to compress such data. And there are many algorithms available on the market to do that. The goals are twofold. The first is to reduce the data storage requirement. Obviously, you have a huge amount of data you want to be able to easily access and control this data, and also you want to be able to share your data with your colleagues. So you want to increase the effective bandwidth for data movement. As I said, there are many methods available on the market, classical methods, and these are based on creating latent codes for floating point type of data. What we propose today is to have even a further compression to binary codes, and this is well known to be an NP-hard problem. As such, it's very hard to solve. And the algorithm we propose, it's a heuristics based on quantum annealing. So let's give a simple overview of the problem. So suppose you have a lot of data. In this case, we consider them to be vectors x, real numbers of length d. You have n samples of them when n is a huge number. And we'd like to have a representation of these vectors through a common matrix phi. Think of it as a basis for the representation of the dimensionality d by nq, and this is multiplied by the vectors a, where vectors a are just binary vectors. Nq here represents number of qubits of number of binary bits. These will be optimized so that you can have the best possible reconstruction of your available data. Depending on the connectivity of your hardware, you might, since phi in general, it's fully connected, so it's not very sparse. You require a huge number of qubits, depending on the problem. So you might want to do boosting, which means you break it down into small block diagonal forms of phi, and you can potentially help in the quantum hardware to do this process. For the example shown today, the data that we have, it's about 10,000 samples. The benefit of having this binary representation is that it's a huge amount of compression. And if the number in Q for the latent code is much smaller number of samples, also the phi, which is the only classical part of it, so to speak, will require little memory usage. And you can keep phi as a common dictionary among the users and just transmit A between them. So, yeah. So the algorithm in itself. It's rather simple. One starts with an initial guess for both the codes A and for the matrix phi, or one uses initial guesses, depending on experience and if one knows what works best. Then one does a typical thing done in machine learning, takes a mini batch of size NB from this big number of samples, and then within this batch, we do a two-step procedure. First, we fix phi and then optimize for A. The minimization will be shown in a second, and this is done on the quantum hardware or simultaneous annealing if you want to test the code first. Then you fix A, and then you update phi. Phi can be updated to stochastic gradient descent or your preferred method of choice with a given learning rate. So this is completely classical done on classical hardware. So it's a hybrid of feedback loop between classical and quantum hardware for this optimization process. And one repeats this until one minimizes the cost function, which is a reconstruction error, and goes to a plateau that you get hopefully the best possible answer to your question. Before going forward, let's look at the actual data that we have in our numerical experiments. The data that's shown here is taken from lattice simulations. I will not go through the details of the data itself because there is no need for, but suffice to say that we have two groups of data. One is vector data and one is axial vector data. Here we've shown the correlations of the various elements of these vectors among themselves. And as we can see from the plot on the left, there is a big amount of correlation in the vector data, but there is a small amount of correlation in the axial vector data. And this is important because this will affect the compression itself, the compression algorithm, as we will see in a second. So, how do we want to quantify the quality of this compression? One could simply say, well, we have a cost function, which is a minimization process, right? You minimize the phi, you minimize the a, and you do this back and forth, and that should be a good estimator. That's true. But because your data can have a lot of noise in it and a lot of variability in it because of this noise, you want to keep control of the noise within the data itself. So what you're doing here is an average of the variation of the reconstruction over the variation of the original data. And the same thing is done in the original step, in the initially, where you try to normalize the variance in the data itself as a pre-process, so that you can keep control over this procedure. And as we show in the paper, this can be connected to the reconstruction error. And this is a quality feature that allows us to say how well we're actually doing in our compression. So this is something to keep in mind, and usually it goes hand in hand with the reconstruction itself, from what we've seen from observations. Due to the limited computational time on the hardware, and also to test our code, we first started with simulated annealing, which is a different heuristic, but also works on binary data, and we use the sampler available from the D-Wave Ocean Library. In order to find the best solution, one would have to run the simulated annealing for a long time with a very small cooling scale, so cooling rate, so that one can actually find the global minimum. But in practice, one might want to wait such amount of time. So what we did is that we ran about 150 samples from a given initial starting point, and then we find the minimum energy, and that's the one we store for AK, and then we repeat this procedure by doing gradient descent for the phi. And what we would like to do ideally is to do this feedback loop also on the quantum hardware, meaning back and forth between finding the best A available from the samples that you collect and then getting phi back and forth. But due to time restrictions, we opted to get the phi this way from simulated annealing and then use this phi and just optimize A directly on quantum hardware. So it's not a proper feedback loop. That's something we'd like to do in the future. But it's a first step that at least allows us to see how well the quantum hardware is performing. We compare this with a PCA, principal component analysis, and also with an autoencoder. So, what do we see? Here we have reconstruction error for both vector and axial data. In blue we have the binary compression, and in green and red we have PCA and autoencoder. Here we are comparing apples to apples because we have converted our floating point latent codes into just number of bits that we need to store. And as we see, binary compression is way more effective than the other methods. And it's more effective because it gives you better reconstruction error, and also it requires much less memory in general. But this was obtained with simulated annealing. Then we compare simulated annealing results with D-Wave. And this is done on vector on the top and axial at the bottom. Number of qubits is given to the left. These are the encoding number of embedding qubits. These are logical qubits. Since our phi was optimized on the simulated annealer, not on D-Wave itself, we had different choices of how to deal with embedding or encoding this phi into the annealer, because this phi will give rise to the Ising coupling and the bias term in our Ising Hamiltonian, right, into our QUBO version of this problem. The first step was just to keep phi as is, meaning whatever the range of the values obtained by simulated annealing, we try to do our best to embed it into D-Wave. Of course, this will give uncertainties because one has a certain range that one can apply for H and J. So one might have very small numbers which end up becoming effectively zero and not having connections where they should be. On the other hand, we normalized our phi. So this is the second column to the right, where with maximal element it's of order 1. Again, This one does slightly better than the previous case. Simultaneous annealing gives the ideal trend, where as you increase the number of qubits, you always perform better in cross-section error. And while D-Wave, this was, I believe, was obtained with 2000Q, so the older topology, and I have later some results with new topology where you compare, but this is the older one. That's something to keep in mind. You have an optimal number of qubits where you start seeing the trend at improving, and then it decreases. This is simply because of connectivity issues, meaning you have, these are logical qubits, and the number of physical qubits that are required for these, I believe, go for the older hardware, go in, older topology, they go into the thousands. And when you have so many physical qubits that have to represent the same logical qubit, you might have noise coming in addition to dealing with encoding of H and J. One thing which would ameliorate the procedure is to do a feedback loop directly, starting with doing everything on the quantum hardware, meaning quantum hardware for A, and then doing it on the classical for phi, back and forth, rather than obtaining the phi from simultaneous annealing. Because you're working with the same precision, and hopefully that self-consistent loop should give you the optimal H and J naturally, as you optimize also phi. So now it's time to compare these results between the two different hardware. What we have obtained here are the plots. First is for the axial vector data. This is the cumulative distribution function, the CDF, where we plot in blue the new topology of advantage, and in red we have 2000. And we have on the left, we have an encoding of 32 qubits, while on the right we have of 60 qubits. What we see from the CDF, from both trends, both hardware, we see that 32 qubits is actually, so to speak, the soft spot. Like that's like the best number that we see, because with 60 qubits we have, again, the connectivity issue that we have too many physical qubits we have to deal with. When we made these plots for each run, and we do about 1500 to 2000 samples per configurations that we just collect data from, we do a different embedding each time, so that we run the heuristic solver to find a different embedding, so that we can avoid any possible bias in that way, just the embedding bias. At the same time, when we embed and we get the result back, we don't use any post-processing from the solver. We just get the raw number, like just the raw values of the qubits, and we check ourselves whether those physical qubits, let's say those 10 physical qubits that have to behave like the same logical qubit, return the same number. This way, we do like sort of cleaning of the result of the samples that we get back, and we only plot the physical qubits. So these are those results for which the physical qubits behave exactly like the logical qubit they're supposed to behave. And these plots, we have emphasized only the low end of the result, meaning the small reconstruction error. If I were to plot this further out, we'll see that the peak is at a suboptimal region, and the peak for the advantage is always, in general, better than the peak for 2000 because it's closer to the value of 0, which would be your ideal, because you have, there you have no errors whatsoever in your reconstructions. Here, I've also had an inset where I'm zooming in into that very, very, very end tail of my reconstruction, trying to see what I get there in terms of distribution. Keep in mind that when computing the Q values, like shown in the previous table, as shown here, the Q values obtained here were obtained only with the best sample that we obtained from here. So it will be at the very end, very, very close to 0. But the study that we're doing here, we're just trying to see how are even the suboptimal solutions spread out, meaning where is the range of the spectrum that we're getting from doing this normalization procedure. And as we can see, having higher connectivity performs better when the number of qubits of the embedding is about 32. So you always have better distribution. This result is for the axial vector data, and this result is for data that doesn't have a lot of correlation among it. So each sample is representative of what you're trying to measure, in our case, and there is no noise coming from Monte Carlo itself here. When we turn our attention to the vector data, the results change quite significantly. First of all, let's just look at the y-axis between the vector data and the XR data, which means tells us how far we can go into our CDF within this narrow range of reconstruction errors from 0 to 1. And as we can see, for 32 qubits, here we can capture about, especially with advantage, we go up to 50% of our distribution within a narrow range of 0 to 1 in our reconstruction error. And this is the average reconstruction error, right, for all these qubits. And this is actually a very decent result, if you think about it, right? Because this is spread, but it's very, very close to the optimal solution. While here, the spread changes for the 32 qubits because we go by a factor of 2 below being reduced. And we see that while the advantage still outperforms 2000Q, the distributions are close to each other in this optimal region. When you further expand out, which I didn't do here, you can see that actually advantage is still better than 2000, but the peak is a suboptimal region. And when you zoom in into the cream de la cream, so to speak, region, where you're trying to get almost close to 0 in your error, you see that the distributions are very, very comparable. And the same thing happens also for 60 qubits. 60 qubits, actually here, we see that they're peaked at suboptimal regions. And this shows by the fact that CDF is actually rather slow value in the percent level, while previously that goes up to 30%, even for 60 qubits. And the difference between these two results has to deal with the type of data that you're actually encoding. The vector data, if we could go quickly back, is highly correlated. And this high correlation of the data comes to bite you back, so to speak, later when you're actually trying to do the embedding, which is counterintuitive, but actually that's what the case here. Surprisingly, specifically for this specific data set here, for the vector data, many samples were accepted. So there is a lot of samples that are feasible, which is great, but the optimization gives it to suboptimal region. And one guess that could be also because of the fact that the PHYs, when they were optimized with simulated annealing. So they were optimized on a classical solver where you could have potentially arbitrary precision of embedding. And that might give you values of phi which are not optimal to be used on a quantum hardware. That's why in the future, we would like to repeat the same procedure of doing optimization, but actually doing it directly with the quantum hardware from start to end. So when we go, and if I could, sorry for switching back and forth, but when we go and repeat this procedure in the algorithm, we'd like everything to be done within quantum hardware for the quantum part, so for the binary optimization, and classical for the rest, rather than doing this simultaneous annealing. Perhaps simultaneous annealing can be used as a warm start to save time for computations, but consistency is one issue which one needs to check here. And okay, so I believe the results speak for themselves. This is promising. It's useful. Another hyperparameter which we actually played with, but I didn't show here, but it's worth mentioning, is an overall chain strength multiplier that we played with the data. It turns out that when you deal with 2000Q, and I believe also previous talks have shown, one has to increase the strength of that chain strength multiplier to increase the connectivity and to increase the quality of the result. For advantage, one doesn't have to do this. So one doesn't have even to apply this kind of hyperparameter. Actually, if you increase the strength, you end up damaging the quality of the result. Because what it does, effectively, it turns the higher numbers into very high, and some of the smaller numbers are effectively 0. So it actually is counterintuitive. One shouldn't do that. It also tells you that for this new topology, you don't need to worry too much about hyperparameters as much as you might have done so in the past, provided you keep your phi within a range of that you can represent with your hardware. So with this, I would like to come to my summary slide. So this is a first foray in trying to do data compression into binary format. Now, data compression in the past has been used widely in classical settings. One can have floating point data sets, and machine learning, like in forms of autoencoder, like we showed, also has been used, and it does better than PCA, for instance. But by doing binary compression, one has many advantages, provided one can do so successfully. The first of all is that you have a much better compression, as simply because you have, as we showed by our results with simulated annealing. So that is very beneficial. And also, you not only have a high quality of the reconstruction, but it's easy to transmit now the data among various servers, and specifically when you have, for instance, other data coming from experiments like at CERN, or in this case we're dealing with quantum Monte Carlo calculations, or even for big data for industry, that's much more useful to have small amounts of data that you can compare with each other. As long as you have a hold of phi, then you know what the data actually means in the real world. We did a linear encoding here, so to speak, which has some advantages for the calculations that we need. But in the future, we'd like to explore also doing non-linear encoding, but with binary written codes. That's a challenge in itself, but it's possible. The results so far are promising. Of course, there is integrated control error of the QPU, which gives you H and J uncertainty parameters, and those have to be controlled. But what's promising is that when you have this higher connectivity, you also have a better embedding, and that gives you overall higher quality. With that, thank you all, and what kind of questions you might have, please reach out later by email. And also, I'd like to thank the other people. Thank you all.